This is, dear friends, the promise of the quantum telescope, which would let us look at an exoplanet 100 light years away. We will see things on its surface with a resolution of about 50 kilometers, that is, just like these images of Earth. And if we look at the moon, we will see objects as small as a thread of... Here is the plan for today's video. First, we will talk about regular telescopes and their diffraction limit. Then, however, we will talk about stellar interferometry, meaning how we can overcome the diffraction limit. Then we will talk about the trick we need to build a quantum telescope, namely quantum teleportation. And after that, at the end of course, we will build a quantum telescope together. So stay with me. I know the subject might be complex, but I'm sure you are among the smartest YouTube viewers in Romania. That's why you landed on this channel. Did you get a telescope but can't zoom in enough? That's because of diffraction phenomena. Here you have the formula that essentially represents angular resolution. Yes, so angular resolution is how well you can see in different directions, depending on d, which is the diameter of the mirror, and lambda, which is the wavelength. In this case, it would be about 500 nanometers. What is the wavelength of red light? The formula that I actually remember and is useful for you as well, and which actually comes from here, is the following. The maximum magnification of a telescope is approximately twice the diameter of the mirror in millimeters. That is, my telescope, for example, has a mirror of about 150 millimeters. That means it magnifies at most, at the very best, 300 times. In practice, what I've noticed is that it magnifies best at about 150 times. That's also because maybe it wasn't built so perfectly, but also because I live in the Netherlands and I have light pollution. Let me give you an example. Here's Jupiter, which I photographed under the best conditions, yes, with this telescope. And you can see here the Great Red Spot, which, pay attention, I didn't photograph directly. I made a vlog of the planet Jupiter, and then I used a software, I think it's called Registack, which analyzed the whole image and produced the best image of the planet Jupiter with my telescope, and you can see here the Great Red Spot. But let's imagine we have an optical telescope with a 10-meter mirror. These would be the best optical telescopes on Earth, pay attention. What would the resolution be then? What could we see on the moon? And here is a calculation done with CIGPT, which tells me that the resolution with which we can see objects on the moon is about 2030 meters as seen from Earth under ideal conditions. This is a photograph, I found it for you. It's a photo taken by the Very Large Telescope, so a large optical telescope with a mirror of about 8 meters. Yes? And at the top you can see a lunar crater that is about 10 kilometers in size. 10 kilometers. If we zoom in a bit and look for some information, we see that the resolution of this image is about 130 meters. So it's basically 5 times worse than we would expect under ideal conditions. So it has a worse resolution because it performs about 5 times worse than we would have expected, most likely because of atmospheric conditions. The image was taken from Earth and the atmosphere creates turbulence. Imagine that instead of the best optical telescopes on Earth, which have mirrors about 10 meters in diameter, we built an optical telescope that would cover the entire surface of the Earth. Well, its diameter would then be approximately equal to the diameter of the Earth, about 10,000 kilometers. So this means that the diameter goes from 10 meters as it was before to 10,000 kilometers. The diameter is 1 million times larger. And this means that the resolution will be 1 million times higher. If before we were looking with that 10-meter telescope and could see objects on the moon under ideal conditions with a resolution of 20 meters, now that resolution will be 1 million times smaller. That brings you to 2050 micrometers. What is the size of a hair? So in other words, with that telescope we could see objects on the moon that are the size of a hair. Now let's say we take our regular 10-meter telescope and look at planet K218, where it said there could be life. It's about 100 light years away. We look at that star system. What will we see? CGPT tells us the telescope's resolution. In ideal conditions, it's half of an astronomical unit. That is, an astronomical unit is the distance between the Earth and the Sun, and the resolution is half of that. So, if we look at that stellar system, we'll probably see the star as a point, the planet, if it's a bit farther away, as a point, and probably another planet as a point. We will only see the planets as dots. I wanted to check this, so I looked for a photo taken by one of the best telescopes on Earth, the European Southern Observatory, right? And here you see the image of a star system located almost 100 light years away. In the upper right part, you can see the location where they say an exoplanet might exist, and the distance between the exoplanet and the star is about 50 astronomical units. You can't see the star in the center because the image in the center was blocked using, well, a blocker, so to speak, because otherwise we would have had too much light from the star. So what we see here essentially is that the star is in the center and the exoplanet is at 50 astronomical units. Astronomice. But the resolution, according to the calculations I did earlier, should be about half an astronomical unit. And it fits, to be honest, that one pixel in the image is about, yes, let's say, a few dozen times smaller than the distance between the star and the exoplanet. So that's exactly how it is. With these telescopes, we can only see exoplanets and stars as dots. Now let's take the case of our ideal telescope, which is as large as the entire surface of the Earth. We do the CGPT calculation and it gives us the resolution. 63 kilometers. So in other words, if we look at a star system 100 light years away, the resolution is 63 kilometers. And I looked a bit on the internet, and to be honest, if I have with this ideal telescope, if we looked at planet K2-18b, where it said there could be life, we would see an image very similar to the image of Earth from space, just like it is here. That means we could see rivers, oceans, clouds, continents, and so on there. We could see the structure of the exoplanet's surface. Well, one last calculation. Here I again assumed we have a telescope as large as Earth. What will we see in the Andromeda Galaxy, which is millions of light years away? Well, the resolution is 0.017 astronomical units. The astronomical unit is the distance between the Earth and the Sun, right? So it's a pretty good resolution. We will see the stellar systems there, right? Pretty well. And the stars and planets, we will see them as dots. But how can we build an optical telescope with a diameter as large as the entire surface of the Earth? Clearly we can't do that physically. We've blocked all the light from the sun. We stayed in the dark both day and night, right? We have to use a trick. Well, the trick we want to use with optical telescopes is essentially the same trick that astronomers used a few years ago with radio telescopes. When, with the help of radio telescopes, they photographed the first black hole in the galaxy M87, if I'm not mistaken, which you can see here, how did they do that? Well, their trick was to take a group of radio telescopes scattered all over the globe, right? So, we could say this, that instead of building a radio telescope as big as the whole Earth, which is what they would have wanted, they used a small radio telescope here, a small radio telescope here, a small radio telescope here, as if they had a big mirror for a radio telescope, but it's missing a lot of elements and only a few elements remain. I won't go into details, I think I have a video on YouTube. But what they did was record the data with each radio telescope and then combine the data together. And to reconstruct, so to speak, the image that would be seen if each radio telescope were a shard from that giant radio telescope as big as the whole Earth. It's interesting to add that they didn't collect the data from all the radio telescopes in real time and then recombine it. As if they had a giant radio telescope, but it only had a few shards. And they took advantage of the fact that the radio waves coming from the center of that galaxy were classical radio waves. And since they were classical radio waves, you don't necessarily have to combine them in a measurement system. You can record each one separately, because I think that's how I understood it. You can record the phase, right? So you can record all of them separately, measuring the phase of each radio wave, and then combine all this data on a very, very classical computer. That's one thing. And the second thing I want to add is that if you try to get an image from a telescope, in this case actually a very large radio telescope, but you only have a few fragments, so you don't have the whole radio telescope, just a few fragments, you won't immediately get the image you need. You'll get a fragmented image. Now in this case, in order for them to get at least some kind of image, they also added some modeling. To build a quantum telescope, we basically have to do what the researchers did with these optical radio telescopes when they measured the black hole. That is, we need to have several optical telescopes scattered across the surface of the Earth, right? And to consider that each optical telescope is a small shard from a very large mirror that would stretch across the entire surface of the Earth, right? And then, just as the light rays that come onto the large mirror of the telescope are combined on a photodetector, this time we would need to take the light rays that fall on different shards and bring them together in one place to combine them. Pay attention here, we can't use the method of radio telescopes, which, as I mentioned earlier, measured the signal in one place and recorded it on a hard disk. They measured the signal in another place and put it on a hard disk. Then they took all the hard disks and brought them to a data center and analyzed all the data. They were able to do this because the radio signal coming from far away was a classical signal. That means they could measure the phase of that signal. But with optical telescopes, we can't do that because light's electric field varies extremely fast and we can't measure it. So then what we have to do is take what it measures, or let's say what it works with, the light that falls on a small telescope, on a chip, yes, and take it to an area. We have to take the light that falls on another optical telescope, so on a chip, and take it to an area. And combine all these light rays on a single detector, just as it would have been in an ideal large telescope. Combining the images from several optical telescopes on a single detector, yes, that's called stellar interferometry. And we will talk about stellar interferometry, but first I will talk a bit about regular telescopes so that we can later understand the principle behind stellar interferometry. The principle of stellar interferometry can be understood if we start with the assumption that there are only some stars in the sky. So we have a star right in front of us, and then the light from that star, the light rays coming from that star, are parallel, and they are parallel to our observation system. And let's say we have another star in the upper right. From there again parallel rays come, all those rays are parallel, but they come from a different direction and reach our measurement system. And here you see two, computer simulations. In the first one we see how the light rays come straight from in front of the photodetector, yes, and pass through a lens, and they are focused into a point in the focal point of the optical system. In this image you see how we are looking at a star that is off to one side, yes, so it is at an angle. From there the rays still come in parallel. They pass through the lens. In this case we can imagine that it is the objective of a telescope, yes, and the light rays meet at a point. In fact, that's how we learned it in high school. That point is, pay attention, in the focal plane of the image. So, in other words, if we place a photodetector in the focal plane, yes, the light rays coming in parallel from the front of the system will all converge at the center of the photodetector, and there we will see a white dot, yes. After that, if we have another star higher up, the rays also come in parallel from that star, but they will converge at a focal point that is lower on the photodetector. And we will see a white dot like that as well, and the rest will be black. So this is what imaging means. Because of this, on the camera's photodetector we will see two separate white dots and the rest will be darkness. And to convince you, here are two images of binary stars, yes, just stars that are very close to each other. The first one is called Albireo, and the second one is called Almach. What is stellar interferometry? Well, we should start with Young's experiment, the one with the two slits. You see here from the left comes a plane wave, so that means it's from a very, very great distance. Here the rays are parallel, yes, and it's a plane wave that travels parallel to the optical axis, yes. And that plane wave passes through two slits, then those waves interfere constructively and destructively, and on the right side you can see an interference pattern. Key here is that the maximum of the interference pattern is on the optical axis, meaning the center has constructive interference. Beyond that, interference alternates between destructive and constructive. This is the interference pattern. I honestly tried to find such an image. With plane waves that are not parallel, yes indeed, so the optical rays are not parallel to the optical axis. And the rays that come from the stars come at an angle, as we saw earlier. So in this image, I should have had a plane wave coming at an angle. So you should have noticed on the right side, maybe I can draw it, I don't know if I can. You'll see on the right side how the interference fringes go up or down. Here we see what a stellar interferometer looks like. The light comes to both the telescope on the left and the telescope on the right. After that, through some mirrors, it is combined on a detector, an image detector, meaning you can see an image there, yes, at the bottom. Well, at the bottom, an interference pattern is created. An interference pattern forms because, like Young's double-slit experiment, the two mirrors act as slits and let light create this effect. So what does that mean? Well, it means that if the light comes straight down, so the light comes directly from above, yes, so I'm standing, it's right above my head, then it will create on the image detector, it creates sus, da, deci steaua este deasupra capului, atunci se va crea an interference pattern, which is centered right in the middle, right? And if the light comes from an angle, at an alpha angle, the interference pattern is shifted to one side, right? By a value that is alpha over 2. It's interesting that astronomers first built this stellar interferometer for a specific purpose, namely to directly measure the diameter of stars. I read a bit about this. I'm not exactly sure why the calculation is like that, but essentially what they're saying is that if we look at the interference fringes and see how quickly, how fast they decrease. So if we look at the envelope of the interference fringes, it is also a measure of the star's diameter. This way, can we directly measure the diameter of the star? On what principle are stellar interferometers built? Well, essentially on the principle of combining the images coming from telescopes, from multiple telescopes, into a single place. We see here, oh, I think this is a drawing of some optical telescopes that exist. So they are the Very Large Telescope, and there we have 4 optical telescopes whose images are combined into a single place. We see here the principle of the system. Essentially, the image from the first telescope passes through a kind of mirror and so on, and reaches a measuring point. The same occurs with the image from the second telescope. Both images reach the same detector, in this case located in the interferometry laboratory. And here is a very beautiful image showing the path taken by the light rays that leave the telescope and reach the measurement location. And here is an image measured using this method. We see a nebula, Eta Carinae, which has 2 stars at its center and on the right side. I think it's the area in the middle where they say they managed to find very strong stellar winds between the 2 stars. It's a stellar wind from one star that collides with the stellar wind from the other star. What's the problem with stellar interferometers? As we've seen, a stellar interferometer is a combination of several optical telescopes, which we can think of as shards of a mirror from a larger telescope. So instead of having a bigger telescope, we have a shard here, a shard here, a shard here. And the greater the distance between these shards, the better the resolution of the images. Good. But in practice, the problem is that if you move the telescopes farther apart, it becomes increasingly difficult to bring the light from all the telescopes to the same central area, where the light needs to be combined. And from what I read, the maximum distance is about 100 meters. So if there's a 10-meter telescope here, another 10-meter one here, and another 10-meter one here, you can place them about 100 meters apart. So basically, it creates a telescope with mirrors. A mirror of about 100 meters, of course. Of course, you only have some fragments, but then the size of the mirror would be 10 times bigger, which means that the resolution is 10 times better. To build a telescope with an area as large as the surface of the Earth, because that's what we want, we would have to take the telescope's small components, the shards, so to speak, of the mirror, which are just a few, and move them thousands of kilometers apart. But this time we can no longer bring the light from one and the other to the same place because it gets lost along the way. And this is where quantum telescopes come in. What do quantum telescopes do? They essentially use quantum phenomena, quantum teleportation phenomena, to combine the images from telescopes even if they are thousands of kilometers apart. So how does a quantum telescope work? Essentially, it's a combination of telescopes that are spread out across the surface of the Earth, and each telescope is a shard of a telescope that would be as big as the entire Earth. And the images, or rather let's say the light that comes from the telescope, from each telescope, so from this one, from that one, from that one, all these rays of light essentially are brought together into a single point. But they're not brought together through tubes, but through a quantum teleportation system. That is, we copy the quantum properties of the photon that comes to a telescope, and through quantum teleportation, we teleport them into the detection chamber. Again, we copy the quantum properties of a photon that comes from the other telescope, and through quantum teleportation, we teleport it into the detection chamber. And there we can imagine that they will interfere and create for us the image we want. In principle, this method gives us extraordinary resolution. As we have seen, we could see a strand of hair on the moon, or we could see with a resolution of 50 kilometers on an exoplanet located 100 light years away, right? That's in principle, because in practice, of course, if we use them here on Earth, we'll have problems with something else, the atmosphere, and probably what will happen is that these systems can also be placed in space. And if you put them in space, that becomes very, very interesting. Then you can increase the distance between the telescopes from thousands of kilometers to millions of kilometers, and eventually even to tens of millions of kilometers. So basically, to put one telescope near Jupiter, one near Saturn, and so on, scattered throughout the solar system. And if you manage to do this and create a connection between them using quantum teleportation, then pay attention, you can have. For the resolution of a planet located 100 light years away, the same resolution I calculated, that Google Maps gives us for an image of Earth. So, you looked at an exoplanet located 100 light years away, just like you look on Google Maps when you look at something on Earth. In practice, there are a few fundamental problems. First of all, you can't combine all the images, so you only have some fragments. Secondly, because you're using photon by photon measurements, photon by photon, you need a lot of photons in order to get that clear image. So I imagine that basically means measurements for objects that are brighter. On the other hand, photon by photon measurement also has an advantage, namely it gets rid of noise. I don't have details about this. But it seems somewhat logical to me, because when you use quantum correlated photons, you eliminate unwanted noise, let's say, from the surrounding light, just like we have problems with city lights when we want to look at distant planets. Well, that light from the city is automatically filtered out by these quantum systems. This idea of quantum telescopes, I think, became widely discussed about 10 years ago, and here I have the title of the article that, as far as I understand, had a very big impact. And from this article, I took two pictures that I'll use to explain how the system works. Here we see the first image from the article. We recognize the two telescopes just like in stellar interferometry, and at the bottom we can see the place where the two images are combined. But pay attention, in stellar interferometry we had an image array, meaning we obtained an image. At the bottom we had, let's say, about 1,000 pixels by 1,000 pixels. But here we only have a single pixel, essentially the central area of that image array, so we have just one pixel. It's just that what we see on the right side, we see that delay area. So what does that mean? It means this: if the light comes from above, straight down, according to interferometry, we would have a maximum in the central area. So if that delay is 0, meaning that light delay is 0, in this case we would actually be in the center area and we would be in the maximum interference zone. And the maximum interference is measured with this system, which essentially contains a beam splitter in the center and at the back. This means mirrors and two detectors to determine when one detector gives a signal, one and the other gives 0. So in other words, if we have just one star above us, the light of a single photon comes in the form of a wavefront, since we're already talking about quantum mechanics, so that wavefront of the photon comes and is recombined on the two detectors. Then at 0 delay 0, the detector will output one, meaning it will detect the photon, the other one will not detect the photon. If, however, pay attention, the light comes from an angle, then we'll get a probabilistic outcome, meaning detector 1 will sometimes give 1, sometimes 0, detector 2 sometimes 1, sometimes 0. That's because essentially the interference pattern is shifted. It's displaced to the left or right, just like we saw with regular interference. And this is compensated for in these telescopes with that delay line where it says delay. That means we adjust the light delay until on detector 1 we always detect the photon, tap, tap, tap. And at the same time on detector 0 we don't hear anything. That means we're once again in the center of the interference zone, and that means the delta delay gives us exactly the angle at which the light from the star is coming. So basically we're scanning the interference zone using that delay, and we see where the maximum is, right? And from that maximum we can figure out the angle at which the light from the star is coming. And how does a quantum telescope work? Here is the second picture from the article, and we'll discuss this one in more detail. At the top, we recognize the wavefront of the light coming from the star. At an angle phi, this wavefront is captured this time by two telescopes. One telescope is in position 1. The second telescope is in position 2. However, this one is a quantum telescope. It measures the quantum properties of photons, the particles of light that come from stars. So this time, we'll look at the wavefront as actually being the quantum superposition of a single photon coming from a distant galaxy, and which is found simultaneously both in position 1 of the left telescope and in position 2 of the right telescope. At the bottom, we have a special source. It sends out only a single photon, but this photon is also in quantum superposition. It travels both to the left and to the right at the same time. So when it reaches the detector, on the left side or on the right side, that photon will be in a quantum superposition. It will be both in position 3 and in position 4. Both on the left side and on the right side, we also see some detection systems. Formed by two detectors each, they are able to detect a single photon. So we have two photons, one that comes from above and is in a quantum superposition between position 1 and 2, and one that comes from below, which is in a quantum superposition between position 3 and 4. Here is the mathematical formula for the quantum superposition state of the photon that comes from above, the astronomical photon. It is a quantum superposition state. That means it is both in position 1 and in position 2, and we also see here a phase term, the phi term. This phase term is essentially given by the angle phi at which the photon comes from the stars. Let's say it comes from the stars. Yes? This is what we need to measure, because if we know phi, the phase difference between the two elements of the quantum superposition state, then essentially we have measured the angle at which the photon comes from the star. So we have measured the angle at which the star is seen. Look also at the bottom. And here we have a quantum superposition state. The photon is both on the left side, meaning position 3, and on the right side, position 4, except that a phase term appears here too. This time it's a delay, an intentional delay introduced on one of the arms, right? And this delay is controlled, let's say, by a button. And it is introduced intentionally, because I believe if I think a bit further, if we manage to make a measurement where delta equals phi, as a result of that measurement we know delta since we know and read the delay. and then that delay is exactly equal to phi. So it's the angle at which the light ray from the star comes in. Now let's suppose the system is perfectly aligned. That is, if the astronomical photon arrives at 1, it arrives at exactly the same moment as the photon that would have left from the bottom one, right? Which would have gone to the left and would have arrived at 3, so 1 and 3 same moment in time, the same on the right side, 2 and 4 same moment in time, right? If we now look at the state of the two photons from a quantum point of view, so we have a system of two photons, we will see that essentially there are 4 combinations. So the total state of the two-photon system is a quantum superposition state in which the system is in 4 situations at the same time. Either we have 1 and 3, so the astronomical photon on the left, the photon below on the left, or we have 1, 4, or we have 2, 3, or we have 2, 4. There is always an astronomical photon, a lower photon. It's just that there are 4 combinations because the astronomical photon can be on the left or right, and the lower one can also be on the left or right. So we have a photon at the top in a quantum superposition state between 1 and 3, and a photon at the bottom in a quantum superposition state between 3 and 4. We want to measure just one thing, the phase phi of the photon at the top, the astronomical one. In practice, we choose a delta phase for the EPS correlation system and then continuously measure photon coincidences, recording all the data. After the measurements are finished, we select from the measured data those in which only one click was heard on the R1 detector on the right, let's say, and on either of the L1 or L2 detectors on the left. These measurements can be interpreted as successful Bell measurements. Quantum teleportation theory tells us that in the case where R1 clicked and R2 did not click, we had a successful quantum teleportation measurement. In this case, the quantum properties of the astronomical photon arriving at 2 are copied into the photon at position 3, which arrives on the left at detector L. Furthermore, the measurement there is a stellar interferometry measurement with interference between 1 and 3. If the delta delay is equal to the phi phase, the interference will be maximal, which means that only one of the 2 detectors will click, always the same one. So essentially, we need to adjust the delta delay until we reach the situation where, in the selected measurements from R1, the successful Bell measurements, only one of the 2 detectors, L1 or L2, always clicks. Then, the value of delta is equal to the value of phi. The key is, as you can see, the quantum teleportation interpretation given to the measurement. It is possible here, I believe, due to the indistinguishability of the photons. I've also covered quantum teleportation in the physics book Told as a Story, where 2 photons are correlated. Whereas here, the EPS correlation source puts only 1 photon in a superposition state, either to the left or to the right. In practice, this is done by sending a photon toward a mirror, and in the classical interpretation, it either reflects or passes through the mirror. In the quantum case, it does both things simultaneously. And we've reached the end of this video, a video that I would say is full of frustrations today. Here are the articles I looked at, including the one I referenced, and all of them were hard to understand. I realized what it truly means to be a researcher, to do your job properly, to understand such an article, right? To really understand it, it actually takes you a few days, because you have to look at the references, you have to understand every point and so on. And this is essentially what research is about. I also realized why my videos where I speak freely end up being very long. Many times for me it's a joy because I read those articles and I actually enjoy it. I learned something new. I've already adjusted my way of working because before I record, I go through the articles I read, take the pictures, and put them in a Word file. So that when I have to refer to something technical, I can show you those pictures as well to make things clearer. Well, and with that, we've reached the end of today's video. I'm Christian Presura, Physica Povestita, and you are cool. If you haven't subscribed yet, you can do so by clicking this subscribe button. See you next time. Until then, I wish you all the best. Goodbye.